Hello everyone, I am the reporter today for our work on the Web Conference 2022, which is entitled The Off-Policy Learning over Heterogeneous Information for Recommendation. And my name is Xiangmeng Wang, and I'm from the University of Technology, Sydney. In today's presentation, I will mainly talk about our work by the following aspects, including firstly, the background of the BIOS issue in off-policy learning setting, and secondly, I will introduce our motivation for debiosing the recommendation system with context information. Then I will give the methodology of this work and follows the evaluation. And lastly, I will make a conclusion about the contributions of this work. Firstly, I would like to introduce the reinforcement learning-based recommendation and illustrate why the off-policy learning is important in the recommendation system. The reinforcement learning-based recommendation is mainly developed for handling the user interaction dynamics. And given this toy example of the reinforcement learning-based recommendation, the recommender first poses some specific actions. For example, some items such as earphones, and then the users may give the real-time user feedback on the post actions such as the click or not. By learning through the real-time user feedback, the recommender can realize the content discovery that adapts with the user dynamics and gain long-term user satisfaction with the system. So the main goal of the reinforcement learning-based recommendation is to take the dynamic user feedback on actions to train the recommendation system, which we call it an agent, for learning an optimal recommendation policy. And the advantages of this manner is unique. Unlike some statistic methods such as the matrix factorization, the reinforcement learning-based recommendation can dynamically learn the recommendations based on user interactions with the agent. And although the advantages of this manner is unique, however, there is a severe challenge for reinforcement learning-based recommendation. Since the reinforcement learning requires the real-time user interaction with user, that means in the recommendation scenario, the recommender should pose some untested actions to users to gain the real-time user feedback. So this way, the user satisfaction with the recommendation system can be terribly hurt and also deteriorate the system profit. To the end, the data collection in the reinforcement learning-based recommendation requires the agent to interact online with the users, which is infeasible and expensive. And on the contrary, the off-policy learning can take the historical user feedback collected by the previous recommendation system and also achieve the dynamic recommendation policy learning. And given this picture to illustrate the off-policy learning procedure, the off-policy learning takes the collected user feedback during the first loop as the input for learning the target policy. And the learned target policy is used for deploy online to maximize the long-term user satisfaction. So the off-policy learning compared with the conventional reinforcement learning-based method can achieve the policy learning through logged user feedback data without interactive access to the online environment. However, we must say that the challenges in the off-policy learning for recommendation is also severe. Here we denote the user feedback collection loop as a login policy and the policy deployment as the target policy. And as we can see from this distribution map, the two policies hold different distributions, which causes severe bias issues in the off-policy learning setting. And the main reason is that the logged data can provide only the partial information, while the rewards for these reactions are missing. And facing the advantages and the challenges in the off-policy learning, next I will introduce our motivations of debiosing the recommendation system in the off-policy learning setting with the context information. There are some existing works that has already investigated the bias correction in off-policy recommendation learning, And the most widely used method is what we call the inverse propensity scoring method. And this type of method usually reweights each sample via the propensity scoring by assigning low propensities to real actions, such as to force the target policy not to visit these real actions. To the end, this type of method will suffer from a really well-known phenomenon, which we call it the poor gets poorer phenomenon. And I give an example illustrating the poor gets poorer phenomenon in this picture. As the real actions can never be visited again with the constraint target policy, and in the recommendation scenario, this manner would result in a phenomenon that a headset will never be recommended simply because it never appeared in the login policy. By doing this way, this type of method usually limited the exploration ability of the recommendation policy and also can terribly harm the user satisfaction by posing wrong recommendation items with low diversity. So facing this phenomenon, we argue that the real-world context information could be useful to infer the missing rewards of the real actions, such that to correct the bias in the off-policy learning setting. And given this picture as an example, the missing reward for the headset in the last example can be simply influenced by incorporating an external heterogeneous information network. So the previous missing headset can be ultimately being recommended for the user. And to this effect, in this work, our investigation is to incorporate the context information in the heterogeneous information network to empower the off-policy learning in the recommendation. And also, we want to develop an unbiased learning objective for achieving the unbiased off-policy learning optimization. Next, I will go detailedly through the methodology of this work. In this work, we proposed an off-policy learning framework over heterogeneous information for recommendation, and we call it the HIM policy. And our framework contains three main components. In the first component, we perform the context representation learning by a co-attentive mechanism on the state, action, and context representations. And in the second component, we perform the HIM enhanced or policy learning by aggregating the context representations to learn the target policy. And in the final component, a counterfactual risk minimization is equipped to correct the discrepancy between the target policy and the login policy to perform the unbiased policy optimization. And next, we will introduce each component detailedly in our HIM policy. And in the first context representation learning component, the first step is the state representation initialization. And in this step, we take the user's historical interaction actions OT as input, and we pass the GRU unit to learn the state representation ST. And in the next step, we perform the initialization of the action representations by transforming the one-hot representation AT of actions into low-dimensional dense vectors. And in the third step, we perform the initialization of the context representation by sampling the meta passes that relate to users and items from the given heterogeneous information network and passes some CNN layers to learn the meta pass embeddings. And by the learned three initialized representations, we finally perform the context representation learning by co-attentive on the state, action, and the context representations. And finally, we can get the user action interaction specific context representations through this component. The second component is the HIM enhanced policy learning component. It firstly incorporates the context, state, and action representations into the uniform context-aware state representation by concatenating each of the recommendations. Then, the HIM-enhanced policy learning uses this context-aware state to parameterize the target policy pi theta by this equation. And in the last component, we approach the counterfactual risk minimization for the unbiased policy optimization. And at the core lies in the clipped estimator. And the clipped estimator caps the propensity ratios, in other words, the importance weight between the logging policy and the target policy to a maximum value to pursue the unbiased policy optimization. And by using this clipped estimator, we can pursue the unbiased policy learning by developing our learning objective in the last equation here. We then give our model evaluation of the proposed HIM policy model, and in the first experimental task, we compare the recommendation performance of our proposed HIM policy with the SODA models, and we can see from this table here that our proposed HIM policy can consistently yield the best performance among all datasets on both evaluation metrics. And the second finding is that although all the baseline models perform the worst on the sparsest Doban book dataset, and however, our HIM policy can still outperform other models since the HIM policy incorporates the external heterogeneous information network information and can handle the data sparsity well. And in the second evaluation task, we perform an ablation study on the heterogeneous information network in our HIM policy model. And we can see from this table here that our HIM policy model augmented with heterogeneous information outperforms the counterpart without incorporating an external heterogeneous information network. And in the figures here, we also investigated how our HIM policy model performs facing different user interaction sparsity. And in these four figures, we divided the users into four user groups by dividing the user interaction with the items. For example, the -600 denoted that the users had at least 600 interactions with the items. And by comparing these four figures, we can see that the HIM policy equipped with the heterogeneous information can outperform the HIM policy model without incorporating the heterogeneous information in different user groups as denoted in these four figures. And also, we can see from these figures that the heterogeneous information has a critical effect on the sparsest Doban book dataset, especially on the sparsest user group, which is the user group with -500 ratings. And in conclusion, in this work, we made the following contributions. Firstly, we are the first to leverage the contextual information in the heterogeneous information network to provide high-quality target policy learning for correcting the bias in the off-policy recommendations. And secondly, we developed a new end-to-end framework HIM policy which achieves counterfactual risk minimization in an explicit manner under the call attention mechanism. And in the experiment part, we generate an online environment using the simulators to carry out experiments on two benchmark datasets, with the extensive results show that our model outperformed the state-of-the-art method. So this is pretty much my presentation today. Thanks for listening, and any questions or comments from the audience?